Okay, so here's my question for you. So if we have 205 grams of baking soda, and I dissolve it in 100 milliliters of water. So with
1,000 or 100?
What was that?
Is it 1,000 or 100?
I'm sorry, 1,000. Sorry, 1,000 milliliters of water. So is this the correct way of making a 20.5% baking soda by mass? So what is percent by mass?
Would it not be grams over grams? Like
grams over grams? Grams of what over grams of what?
The solvent over this.
Is it the solute over the solution?
There you go.
Okay.
Times the 100%, correct? So,
that's right.
So this wouldn't be correct.
That's right. Okay. So it wouldn't be correct. So how can we correct it?
So is the solute the baking soda?
Solute is the baking soda.
So would you put the 205 grams up top?
Okay. I'm not talking about the calculations. I mean, although we have to do the calculations to get the answer.
Okay.
Yes. So the solute is going to be the baking soda.
Mm-hmm.
What was that?
Convert the milliliter.
What am I going to convert the milliliters to?
Grams.
And how would I do that?
Great question.
Isn't 1 milliliter equal to 1 gram? It's a 1-to-1 conversion.
So where did you get that from?
You know what, Dr. Henry, I just remember it from when you told us.
Okay.
I remember it was 1-to-1.
Okay, so what is it that makes it 1-to-1? So you said 1 gram is going to equal 1 milliliter. Is that for every solution or is that for water only?
I believe it's everything.
Isn't the density of water one?
The density of water is equal to 1 gram per 1 milliliter. Good job, Stephanie. Otherwise, I was going to make you guys do an experiment.
That wasn't Stephanie.
That wasn't Stephanie? Who was that?
That was Selena.
Oh, I'm sorry, Selena. Good job, Selena. See, I'm just so used to hearing Stephanie's voice. It's all I hear all the time.
I know.
When I wake up, I hear Stephanie's voice. When I go to bed, I hear Stephanie's voice.
Stephanie doesn't turn her camera on no more. She's shy.
Oh, she's shy.
No, I'm eating right now. I don't want to.
She doesn't want to tempt me. Because she knows I'll be at her door. I'll be,
yeah, I'm actually eating lentils. I'm kidding. No. No, I'm kidding. But yeah, I'm eating.
So yeah, that's right. The density of water is 1 grams per 1 milliliter, right? And so that makes it really nice so that we can do that nice conversion there, right? So if we wanted to sit there and do that, then how much water should we be adding? Well, what is the solution? What is the definition of a solution? Well, first off, what is the definition of a solute? Since you told me that, Ryan, baking soda was a solute. Why is baking soda the solute?
I think a solute is anything that can be dissolved. So,
okay.
and it's like, I think that solute is the major component of your solution.
Is it the major component of your
Or
solution?
minor, sorry, minor.
Okay.
So I know it's going to be dissolved, so that's why it's the solute.
Okay. So then what is it dissolved in?
Water.
In this instance, it's water.
In this case, it's water. Okay. So what is the term of the things that we normally dissolve stuff in?
Is it the solvent?
It is the solvent. So the solution is defined as what?
The combination of both?
Okay, that is correct. So solution is equal to the solute plus the solvent. Okay. So now knowing this, how would I set up this experiment if I was going to make a 20.5% sodium bicarbonate solution, 20.5% by mass sodium bicarbonate solution?
Would you do 100 grams of water? Or it would be your 205 grams of baking soda over your 1,000 milliliters, or 1,000 grams of water?
Okay, so you would do exactly what they did? Is that what you're telling me?
Wouldn't you use the density equation to figure out the grams of water?
Okay, so I need to first use the density equation to figure out the grams of water. Okay, so I have 1,000 milliliters. One milliliter over 1 gram. So I have 1,000 grams of water at my disposal. So what am I going to do?
Can I participate, Dr. Henry?
No.
Still need to add the grams of the solute?
So I need to add the grams of solute. Okay, so I have 250 grams of solute. I mean, sorry, not 250, 205. Okay. Then what am I going to do?
Plus the 1,000?
So am I going to take the whole 1,000?
Well, aren't you mixing it in the 1,000?
Okay.
And
Okay.
then wouldn't you divide just the solute over the 1,205? And multiply it by 100.
this is how you would solve the one for the Kool-Aid lab, Dr. Henry?
Sort of, but this is, it's not volume. This is now mass, but it'll be very similar, yes.
Okay.
It would work in the same way.
Yeah.
Okay, so we have 17.5% sodium bicarbonate. Okay, so is that going to give me my 25% sodium bicarbonate? I mean,
No.
20.5, yeah, said it right the first time. 20.5% sodium bicarbonate. So how would I do it? What would I change to make it right? How would I do it differently?
Dr. Henry, I have a question.
Yeah.
Would you subtract the 1,000 grams of water to the 205 grams of baking soda?
Yes, let's do that. So is that a question or is that a statement?
Question answer.
So if I want a total of 1,000 grams of solution, right? That's my goal. So in that case, if I have 205, how much water am I going to need? $795. Okay, so then I'll need which will be 795 milliliters of water, right?
Yes.
And I would add it into my little beaker, mix it up, and we're good to go. And so if we did it that way, do you mind if I write that in red? We'll circle it in red. If we did it that way, we'd have 1,000 grams over 205 grams times 100. And that should give me my 20.5%.
Wait, so Dr. Henry, so the grams of baking soda is already included in that, on the grams of water already?
Yeah, because we're talking about the solution. We're not talking about the solvent, right? So if you look at it, the definition of percent by mass, it's just the part, is the solvent over the solution. I mean, not the solvent, the solute over the solution.
Okay.
Okay?
Yeah.
And we know that the solution is just a combination of the solute and the solvent. Piece of cake?
Dr. Henry,
Yes, Andy.
you know where you get 1,205 grams?
Because
Under solution and solvent, you know, solution, it's 1,200.
okay, so we get that because we
You mean
added
you plus 1,000 to it? So,
yeah, so this is the baking soda, and then this is the water.
water, yes, 100 ml.
Yeah, because we took the density to convert the water into grams.
Oh, okay. Let me see. Oh, okay. Yes. Oh, okay. A block here. Okay.
Yep.
Okay. 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 Thank you.
You're welcome.
Because my the camera, the screen here blocked it.
Okay.
So the one that you first did, that's the correct way to do it, right?
This here?
No, let me annotate. Like this, like all of this right here. This and like that. That's the correct way that we were supposed to do it, right?
No, because, well, you're supposed to use this information, but this part here is incorrect because we want it 20.5%, right? And then if we did it this way, right, if we did it the way that they explained up here, then we would have done it wrong. You end up with the wrong solution concentration, right? So you'd end up with actually 17.0%. And that's not what we were looking for. Okay, so the point of this, there's two things that I want you to get out of this. First off, to understand what percent mass means, right? And percent mass is just a form of writing the concentration. That's the number one thing. The second thing is that when you're in a lab, you got to think about the procedures that you're going to do. So the way that you would correctly do this, right, is if you wanted to do percent mass, right, you would have to take the mass of your baking soda, right, and you would need to know that. And then you also need to make the mass of your baking soda plus the solute to sit there and get the mass of the solvent. Okay? So let's say, for instance, let's change it up a little bit, right? And maybe it'll get a little clearer. Let's say that we have, so we'll start it off with the equation.
Yeah, so let me see. So you would have the 100 grams on top.
Okay. Okay, so we're going to put 100 grams on top. Okay.
Then you're looking for the solution in grams. And then it's equal to 20.5%. So would you like divide by 100 on both sides?
Why not divide by 20 or multiply both sides by solution? And divide by 20.5%. So that gives us what?
No way.
4.8.
487.80.
487. So, or 400. How many sig figs would we have in this situation?
188. 3.
Oh,
Well, actually, it would be 1, but we'll put a decimal point here. So, just so that we can use 3. Okay. And that will be grams of solution. Okay, so then how much water should I add? Is that the number, how much water we should add, or is that?
So then you subtract it by the 100 grams. Is that the?
That is correct.
wow, you smart. Good job, man.
I think that was Selena.
Oh, Selena, good job.
Again.
Okay. So we need 388 grams of water. Piece of cake?
Kind of.
Try one more. That's fine.
Well, let's get started with the lecture because then we'll get into a little bit more. Okay, but you see how you could use
This
it. Right?
isn't the lecture?
No, this isn't the lecture.
We still got a lot of time with Dr. Henry, Stephanie. I don't know why you're.
I know.
You're
I just checked the time and it's barely 6:47.
And you check how many slides there are?
Check
60 slides to go through, Stephanie.
I know. Let me get comfy.
Are you ready?
Do it.
Yeah.
Excellent. Oh, that's right. You guys started at a different point than the other guys. So where we left off.
I don't even think we started 16. I think you were like making us tell you what a solution was. And
That
you're like,
was 16.
but you never opened the PowerPoint because remember we had like 3
I
minutes
did. I opened the PowerPoint.
left. No, we didn't.
Yes, we did.
No, you were like, oh, we
Yes.
have 3 minutes.
We went over one slide, but we did open the PowerPoint.
We did go over one slide.
And I don't think we got halfway through it.
So am I getting points for agreeing, Dr. Henry? Or?
Yesterday.
Okay. So can you guys see my screen now? It's not a black screen.
We can see the PowerPoint.
Excellent. Okay, so you guys remember what homogeneous mean because we argued about it for about an hour.
Yeah.
And we only have 3 minutes left.
Correct.
Okay. So we know that this can exist in multiple states. So a solution can kind of be a mixture of gas, liquids, or solids, or it could be a mixture of all of those combined, right? So that could be a mixture, as long as it's, homogeneous, uniform throughout the entire thing, okay? It has to be dispersed, right? Meaning that it's staying in solution, it's not dropping out, okay? Or it's all in that one form, it's all that solids or whatever, so that you can't distinguish between it. So it's gonna have to be dispersed like evenly and small, so nothing is separating between the two, okay? And it could be 2 solutions or more, right? Most cases we're gonna be working with is 2 solutions in our case, right? I may try to get crazy every once in a while, but for the most part, 2 solutions. Okay, we've talked about a solute and a solvent, right? You guys told me the definition of that already. See, that's why the discussions are so important, right? Okay, so here we have water, and we have, I believe this is, I'm going to take a guess, but I'm going to say it's probably copper, probably, since it's green, probably, or bluish green color, I'm going to say it's probably copper chloride or copper, something along those lines, okay? So, copper 2 chloride, that's my guess, okay? So in A, which one is the solute? Which one is the solvent?
The solute is the one on the left.
In A, which one is the solute and which one is the solvent? So you said the one on the left is the solute?
No,
That's the
solvent is the one with the, solute is when you mix it.
Solute is when you mix it?
So the solute would be the little blue powder, and the solvent would be the liquid in the
Okay, which is probably water. So we're gonna say it's water, right?
Yeah.
Especially since we have the Mickey Mouse ears here, it's water. Okay, so we have copper 2. This is copper 2 chloride, right? So we have copper 2 chloride. We take a pinch of our copper 2 chloride and we put it in the water. So which one is going to be the solvent again? And which one is going to be the solute? Help me help you.
B?
Not A or B. Which one of these? This guy here or this guy? The water or the copper 2?
So the one on the
Chloride.
far left is the solvent.
So
Yes.
this one here,
Yes.
the liquid.
Yes.
The solvent. You just put A, B, C.
And then this is the
So that S, O. My God, computer
Okay.
not working.
So then when we put it in our water,
That's
we take
the
our pinch and put it in. What is this guy called?
a solution.
Now look at this, right? This is a really good experiment. If you look here, look at the meniscus. Then look at the meniscus here. You can clearly tell that you added more volume, right? So that is the third thing that I wanted you guys to recognize, is that you're going to be adding volume when you're adding your solution. So if you want a particular volume at a particular concentration, you need to bring it up to volume, okay? Okay, you guys ready for the next part?
Yeah.
Okay, so concentrated. So do you guys, have you gone to the grocery store and saw the new Kool-Aid little squirt bottles? The concentrated squirt bottles?
Oh, yeah.
Okay, so that's an example of concentration, where you have a whole bunch of solute in a solution, or I mean in a solvent, right? More than what you would have when it's dilute. So that would be concentrated. Now, when you take that and put it into your Kool-Aid, when you make Kool-Aid, you know, it's diluted, right? So it'll be like 2 quarts of water, and then you put in like half the little can of that concentration of Kool-Aid. Okay, you guys kind of see that?
Yes.
Excellent. So let me show you an example in chemistry. Okay, so here we have copper wire. One, we have a dilute silver nitrate solution. So this solution that's kind of have this, the kind of guess, silvery blue color to it, right? This is your silver nitrate. So now what's happening is that the copper wire is exchanging with the silver nitrate. And so on the wire itself, you're going to get the accumulation of silver on the edges. You guys see the little silver particles coming off?
Yes.
Right. So here we have a whole bunch more silver nitrate. So you have longer crystals of silver coming off the copper coils, okay? Because you have so much more. So you're exchanging the copper, and it's changing to copper 2 ion, okay? And then you're getting the silver metal coming off. So remember the activity series? So can you guys see that?
So what would happen if you were to remove the wire? Would the crystals, like the silver crystals, stay there, or would they just like fall off?
They'll start draping off. Like, so if you shake the wire a little bit, it'll all fall off. But the reason why it's happening there is because you're getting the exchange happening at the surface of the wire. So it's all happening along the outer part of the wire, okay? And so if you shake it off and you pull it out, then all the silver is going to come off. The reason why you have a blue solution is because now you have copper 2 ion, right? So you know what copper metal looks like. I think everything in. So you guys know what copper metal look like?
Yeah.
What color is it? It's kind of like a
brassy color.
Okay, it's like a brass color, right? And so, but when it becomes an ion, it becomes like either a green or a blue or somewhere in between, depending on the ion that you're forming, right? So if it's copper 2, it's typically like a nice little blue color. Okay? Okay. What is solubility? Stephanie, solubility.
Solubility is well, a measure of how much solute you dissolve.
I want it in your own words. Don't read the screen.
Solubility is I don't know, like a certain amount of substance that will dissolve.
Okay, so give me an example.
Because of a temperature. Like probably like water and sugar.
Okay.
Like
that's a good example.
Sugar dissolves like after mixing it like with water, I guess.
Okay, that is a great example. Good job. Okay, so what does saturated solution mean? Let's see. Ro, in your own words. Are you there, Ro? Are you ignoring me, Ro?
It's the solution they give you when it's hot. It melts in the hot. You know? Just like when
say that again?
It's a solution that melts in the hot. When it put a temperature on it, it gets hot and it's melting. It's just like when you're melting the gold
you're kind of right? So you're approaching the right area, Andy. You know, since you're not Ro, but you're on the right ballpark. Okay. So what saturated means? It basically means that you're reaching that limit of solubility, meaning that you keep adding, and you're mixing, and everything is dissolving, right? But you're right at that that line where if you go a little bit over, you'll end up with solution you'll end up with not solution, but you'll end up with a solid at the bottom because you're no longer able to dissolve it, right? So you're just under the limit of solubility. Okay. So that would be a saturated solution, right? So it's saturated, so you're reaching it all the way up to the point where if you go over just a little bit more, it'll fall out of solution. Now, this can change as a result of temperature, right? So if you have a higher temperature, you can get your solution to be saturated, right? Even more. So you can add a little bit more because you're able to sit there and keep it in solution because of the temperature itself, okay, and the effects of temperature. Unsaturated basically is you're less than that limit of saturation, solubility, right?
Oh.
So unsaturated basically anywhere less than solubility. So solubility is that point where you stop being, so the solubility limit is the point where you stop being soluble, where anything over it, it won't be able to hold it. It'll release it immediately, or it'll cause it to precipitate. Okay, I'll show you an example here in a second.
We'll translate it.
Okay, supersaturated is basically, it's going to be a solution that is greater than the normal solubility limit, right? So we have a solubility limit at a certain point, right? And then if we heat up the temperature, it'll cause it to be supersaturated. So if we allow it to cool down, or if we allow it to, just add another drop, it'll totally drop out of solution, okay? So miscible means that it's soluble. Immiscible means that it's insoluble, okay? So here's an example of supersaturation. So here's our solution, right? So initially our solution is all clear and everything like that. It's been saturated with our compound. So we added so much, in this case it's probably salted water. So we've added all of this salt and water, we got it in solution, and we heated it up so that the salt will remain in solution, right? We add 1 little grain of salt. As we add that extra grain of salt, it starts crystallizing, right? And it will actually crystallize almost everything, all the salt that's in there after we've exceeded the saturation limit, okay?
In hot water?
Yeah. Well, you let the water cool off, right? And you can keep it in supersaturation, right? Long as you don't have anything to cause a nucleation of the crystal. But by you adding a little bit more, it causes that nucleation of the crystal. It pushes it over the limit. So as soon as you do that, you actually start forming your little crystal. Okay? Pretty cool?
Yeah. I'll try it.
Dr. Henry.
Yep.
I have a question.
Yep.
Would this kind of be the same idea of making rock candy?
It is exactly the same idea of making rock candy. That's how rock candy is actually made.
Okay.
Yep. Good job.
Oh, this is making...
Hey, Jessica, we got a lab. Gonna write that one down, rock candy. Okay, so miscible, what does miscible mean again?
Soluble.
Soluble. Okay, so A basically shows you a solution that is soluble. So here we have octane and chloroform. So both of these are hydrophobic, so they're gonna be able to interact with each other, right? Because they both don't like water and they have carbon in them, so they're gonna be able to interact with each other with no problem. So in that case, they're soluble in each other. What about water and gasoline? Or oil and water? What was that?
Miscible.
Immiscible.
Immiscible. Okay. Immiscible means that it's not soluble. So you guys know that oil and water don't mix, right?
Oh, candy lab, okay.
Yeah.
Now I know. It's
What
gas
was
on
that?
top. I don't understand why is the gas always on the top of water.
Well, because oils. Why do you think the gas is on top of water?
I always think it's lighter. That's why. That's why it go up to the top.
So the density is lighter.
Yeah.
Yeah. Okay. So, you guys remember what polar means?
Yeah. Polar mean it's like not equal.
Dr. Henry,
Negative charge.
so by the rock candy lab, do you mean like making the little like lollipop crystal candy rock, or making like the actual pop rocks?
Not pop rocks. Rock candy, not pop rocks.
Okay, just making sure.
Although that would be interesting too.
That would be.
Think about
We
that
should
one.
do that.
Pop rocks?
Pop rocks?
How did
Okay.
those work?
What was that?
How did those work?
I actually have to think about it. I haven't really given it too much thought.
I mean,
But it's
wouldn't it
definitely a
have to have
chemical
something-
reaction.
Yeah.
I have to think about what it is that actually is causing it though. I have to do a little research. But that one might be cool. I think that might be cool too. Let's see. Okay, so polar, you were saying, Ryan?
It has positive and negative charges.
No, those are ions.
Wouldn't it?
Charges that aren't evenly distributed.
Evenly.
So what do you mean by that?
So like it wouldn't be like when we were talking about like the geometric thing, it wouldn't be like linear. Like it would be like, so like for H2O, they would be like pulling, it'd be like polar because the hydrogens are pulling on the oxygen.
Like they're more.
Okay.
Oh wait, that might be linear though.
Well, no, it's not linear. Water isn't linear. It's
Okay, never
like
mind.
gravity.
Yeah, so it'd be like pulling on them like in a direction instead of them just like being equal.
Okay, so you're saying unequal sharing, right? So it has to do with that unequal sharing of electrons, right? So it's not necessarily a positive and negative charge, but it's more of a positive and negative pull. You understand? So it's not a full charge. That's the reason why we always use that partial. Remember this? Remember this, Ryan?
Yeah.
Yeah. So the reason why we use that, because they're covalently linked, they're sharing the electron, but who's getting the electron the majority of the time?
Hydrogen.
Hydrogen? Who's the big brother? Look at it. If this is partial, this means partial negative, and this one is partial positive, or if we talk about poles, this would be your negative pole, this would be your positive pole. Where would the electron be most of the time if this one is your negative pole? Would it be hydrogen or would it be oxygen?
Oxygen?
Oxygen. Yeah. So oxygen, remember, we talked about electronegativity. Obviously, I got to put it on the test now. Okay, electronegativity. Dipole. Okay. Got to make sure to put that one on the exam. So, in that case, that's an example of a polar molecule, right? So, but if it was evenly shared, like you were talking about carbon dioxide, which is linear.
Yesterday,
so, is that polar or is that non-polar?
Which one?
Non-polar.
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 Okay. So, and so then that way you don't have a not one side is stronger than the other. or one part of the molecule is stronger than the other. Okay, so here, this guy is pulling in this direction because the electrons are being pulled in that direction. Here, they're distributing evenly. They're sharing evenly. Okay.
M101.
Okay. Okay, so basically you guys know how solutions are formed. Why does things dissolve in water? Why does salt dissolve in water? Because salts are ions, right? Why do they dissolve in water?
Different ion.
Is it because of the solubility?
Okay, is it because of the solubility?
Is it because the positive and then the negative, like the positive in the water and then the negative charge in the chloride ions, they kind of make that, they attract?
Okay, Ryan, just think about what we just drawn. Don't just ignore everything that we just talked about.
They have equal, right?
Oh, because of the polar.
Because water's a home wrecker.
Because water's a home wrecker. And then what were you saying? Was that, who was that? Senwana?
Carissa?
Yeah.
I saw Carissa said water's a home wrecker. Yes, because water's a home wrecker. But Senwana was giving us the reason why. You said water is what again?
It's more polar.
It's polar, right? Meaning that the water molecule here, right, is partial positive and partial negative. So the oxygen is the red, the hydrogen is the white. So where's mine?
Ion is negative charge.
Okay, so those are represented here. The oxygens are going to be partially positive. I mean, not the oxygens, the hydrogens are going to be partially positive, where the oxygens are going to be partially negative, right? Meaning that its pole is going to have a negative pole, okay? So what is the negative pole going to interact with? Is it going to interact with the sodium or is it going to interact with the chlorine?
The negative pole
Mm-hmm.
is going to act with, is it going to interact with the sodium because it's positive?
Sodium, yeah.
That's right. It's going to interact with sodium because sodium is what?
Positive.
Positive. Okay, the sodium is totally positive. So then sodium is going to interact with, let me move this, with the oxygens. Come on.
Oh, is that why, you know, why when we have sodium and like shot on the hand and it get hot something, and the air like usually gets sticky?
Well, not really sticky.
Like
it'll get grainy and kind of watery because it starts to dissolve.
Yeah.
Okay,
yeah.
And the chlorine's going to interact with what?
Which one again?
Chlorine, the chlorine ion, or the chloride.
Just make it.
Going to interact with the positive, so it's going to act with the hydrogen.
Okay, so it's going to interact with the hydrogens.
Nitrogen.
Okay. So these guys are going to interact with each other. That interaction, right? The fact that it's interacting with the hydrogen, that's called the hydrogen bond. So really what it is connecting, and they're kind of like, they have a little bit of an attraction to each other, not a strong attraction, but a little bit of an attraction. So it's kind of like a fist bump, right? So like your fist bump, okay? It's easily broken, but you still are interacting with each other. You're touching each other, okay? So that's kind of like what's going on there. And that's all based upon the charge of chlorine and the partial charge or the pole of hydrogen, right? So if you take a look here, look at the orientation in the figure. So this is chlorine. Chlorine is negative. And you can see that all of the hydrogens are facing towards the chlorine. Do you guys see that?
Yes.
Okay. Sodium is black. It's plus. Who's facing towards the sodium ion?
The oxygen.
The oxygen. Okay. So do you guys see that? You see it, Ryan? Are you there, Ryan?
I'm here.
Okay. I feel like I'm talking to one person every time.
Oh.
I'm just trying to process this.
So, but does that help you see it?
Yeah, the visual makes a difference.
Yeah. Okay, so now this is pretty cool, right? So that means that if you have enough water molecules, you can sit there and surround all of your sodium chloride. But what happens if you don't have enough? Let's say you have a whole bunch of salt. What happens?
Would it not dissolve?
It won't dissolve. So you have salt at the bottom left, right? Piece of cake? Simple?
Yes.
Okay.
Do this the best.
So this is just basically where we're forming a saturated solution. So you can see we have our solute that's here initially. This is our water. As time goes on, and no mixing really is being done here, it's just happening naturally. So in this case, you're dissolving your solvent or your solid there. It's being broken up into its ionic component. At the same time, you're going to reach a point where you're going to start getting more of your solid form as well as the stuff that's being dissolved. And to the point that you reach what we call equilibrium. And that's what's being shown here. Okay? We've gotten to the point where we've saturated our solution. That is as much as it can take. And then now we're in equilibrium. Okay? Are we good?
Mm-hmm.
Okay, so what are things that determine our solubility? Well, one of them is your intermolecular forces. That's your ionic force, that positive and negative. It is the dipole. Dipole is that partial positive and partial negative. Dipole, di, another word for two, pole, so your positive and your negative pole. Okay. We have inner dispersionary forces, right? So that's kind of like what we saw with things that are nonpolar. So nonpolar things interact with each other because they're dispersionary, right? They just kind of not really. They don't like each other so much, but they don't hate each other like they hate water, right? So they'll interact with each other because of that, because they have similar characteristics, okay? And then we have what van der Waals forces, which are the same thing, basically allowing us. Okay, you guys got that? Yeah, no, maybe?
Can you explain it? Sorry, can you say it one more time?
I said, so we have, so intermolecular forces. Basically, it's forces that are interacting between two different molecules. So you know how we've always talked about a molecule and how that hydrogen affects that oxygen? Here we're talking about how the molecule next to it is affecting each other. right? So those are intermolecular forces, right? You don't really need to know all of them, but you want to know the ionic one, and you also want to know like hydrogen bonds and dipole, okay?
Okay.
So those are your two major ones that are going to cause strong interactions and also affect solubility, right?
Okay.
And so depending on how strong that is, the more soluble you are. So if you have things that form dipole or things that are polar, polar things are going to form, are going to be more soluble, where things that are not polar aren't going to be as soluble, okay?
Okay. Mhm.
So for instance, is oxygen gas polar or non-polar?
Non-polar.
What about, that's right, it's non-polar. What about nitrogen gas? Is that polar or non-polar?
Non-polar?
Non-polar. So both of those are non-polar. So because they're non-polar, right, they're gonna, the way that they're gonna interact, like with water, they're still gonna be dissolvable, but they're not gonna be as dissolvable as like sugar, because sugar has some polarity to it, right? It has that carbon and that hydrogen, which is gonna allow it to be, and oxygen, which is just gonna allow it to be polar, right? So our sugar is gonna be more polar than oxygen gas. So you're going to be able to dissolve that into water better than you can dissolve oxygen gas into water. Not that we can't dissolve oxygen gas in water, because we can play with induce, what we call an induced dipole, which is something that you guys don't have to worry about. So the other thing that's going to be a factor is partial pressure. So partial pressure is basically the pressure that's going to be associated with the solute gas. And that's the pressure that's gonna exist right above the liquid. So you have your solvent and you have your solute, right? So you have a gas that is able to go into your liquid, okay? So in this case, you have a gaseous form that's able to go inside the liquid. So this is an example of carbon dioxide. Do you guys drink soda?
Yes.
Yes. So why does soda bubble?
Because the carbon dioxide is being released.
Because carbon dioxide is being released. So that means that we had to dissolve carbon dioxide into our water, right? Because at first it was just sugar water, right? Is that correct?
Yes.
Because if we shake it up and let it sit for a long time and just open up the cap a little bit, what'll happen? It'll
Load.
Well, it'll blow up eventually, but yeah. But after it blows up, what happens to the soda that's inside? Is it still bubbly?
No, it's flat.
No, it goes flat.
It goes flat because it's no longer soluble, or that CO2 has been released, and so we didn't keep any of it, right? And so that's an example of a solute gas being inside of a liquid, carbon dioxide and sodas, right? But if you open up, like if you don't notice at any point that you open up your soda, doesn't it go?
Yes.
That's that partial pressure, right? So because you have this state where those carbon dioxide molecules are going in and out of the liquid, and then they get to a point of equilibrium, right? And so each time you open it up, that partial pressure is going every time, okay? So that's an example of partial pressure. I'll show you another example here in a second. The other thing is temperature. So because as you heat up things, what happens to the molecule or particles?
Move faster.
They go faster. Because you're heating up, you can sit there and affect solubility. The higher temperature you are, or like water, more things are more soluble in it, okay? So you can keep packing in like that salt and packing in that salt if you keep increasing the temperature to an extent, right? Until you boil out all of the water, then that's a whole nother issue, right? Okay. So here's an example, right, of intermolecular forces. So we have ethylene glycol. Ethylene glycol, if you take a look at it, this is the structure of it. So again, the white is hydrogen. The blacks, or the grayish, that's carbon, and the red is oxygen. Because you have those carbons, and mainly because you have the hydrogens and the oxygens, they're going to be forming dipoles, right? and they're going to go into solution with water. Here's water, here are rabbit ears. And so they're going to be interacting with each other because each of them have a slightly positive pole and a slightly negative pole. These guys are also going to have a slightly positive pole and a slightly negative pole. And so they're going to orient themselves to interact with those poles differently, right? So they're going to be able to mix within each other. So we get antifreeze mixes with water. Okay, how many of you guys, do you guys buy the diluted antifreeze or do you buy the concentrated one?
The what?
I didn't hear.
Diluted antifreeze or concentrated?
What's that?
Antifreeze?
Yeah, it's for your car.
I don't buy that.
You got to know, okay, I don't care if you're a woman or not, things you need to know about antifreeze, because you do not want to put oil in your radiator or antifreeze in your oil thing. Those are two things you never want to do. So you need to know about antifreeze and you need to know about oil, right? Those are two major things. And plus you need to know how to change a tire. Those are three things.
I don't even know how to open the hood.
Yeah, no, me neither.
I'm thinking about it right now. If I went to my car, I wouldn't know how to open it.
It's usually a little latch, and then you go under the hood, and there's that little latch you got to push to the side to open up the hood.
And Carissa's independent.
I know, I'm not.
I gotta be.
Wow. Okay, so you guys, it's gonna bite you in the butt. One of these days, you're gonna be on the side of the road.
I'd be calling
you need to know how to change a tire.
Don't jinx us.
I'm just telling you how it is. You need to learn this. These are things you gotta learn.
If I have any car problems, I'm gonna call you.
Oh, they have issues.
I'm gonna say you should have learned earlier.
Just tell him you have food, and he'll go.
Oh yeah, if you feed me, I'll come. That's true.
I got you.
Okay, so where are we? Okay, so in the case of oil and water, right? Again, these guys are not going to be miscible because we know that oil doesn't like water, right? Because oil is polar or non-polar.
Oil. Is it? I am non-polar.
Non-polar. That is correct. So oil is non-polar. It's a hydrocarbon. So it's not going to interact. So they're not going to interact with each other because of that. Okay? And so you're going to get them, as soon as you pour that oil in there, it starts to separate from each other. And so oil is going to interact with oil and water is going to interact with water. It's going to be like, you know, back in the old days where, you know, blacks stayed on one side of the town and the white stays on the other side. Kind of like that.
I understand now.
Okay.
I understand why you put the water in the car don't win no more.
Yes, that's right. And that's exactly why you don't want to sit there and put oil in your radiator, right? You don't want to make those mistakes because that really screws things up.
Wait, so does
You also don't
have this, right?
What was that?
Electric cars don't have this, right?
Oh no, they need, so even electric cars have lubricants because you have things that are moving, but they're moving as a result of electricity rather than moving as a result of pistons and combustion.
No, they still need oil, right?
Excuse me?
They still need oil, not gas.
Yeah, they still need a lubricant. Yes, they do.
Yeah,
So we'll still have to know this even if we have an electric car.
Yes, you do need to know this even if you have an electric car. You can't get away from it. You're like, I'm just going to buy an electric car. That's my answer. As long as I plug it in, it'll be fine. Okay, so here's an example. We have a solution. We have a gas in this canister, and we have a liquid in the canister. So here we have the gas. You can see the gas going into the liquid. So the white balls here represents the liquid, and the red balls represents the gas. So in that case, the partial pressure here is less. You have less partial pressure in this circumstance because you have a bigger volume, right? So the volume here is bigger than this volume. You guys see that?
Mm-hmm.
Okay, so your partial pressure here is going to be less than what it would be in this case. Okay, so here at constant temperature, you're going to have a higher pressure, and you're also going to have more of the gas going into solution. More of it is going to be dissolved in solution, where this guy is going to have less dissolved in solution. Okay? Good, bad, or ugly?
Got it.
Okay. Okay. Okay, so remember I told you about temperature affecting solubility. So this is just basically a table that shows you that. So for the most part, the solubility of salt isn't going to change a little bit too much until you get to a very high temperature. So you can see that it starts to kind of pick up a little bit here. But look at potassium chloride. Or look up sodium nitrate. Okay, so the solubility goes up quite a bit in the case of sodium nitrate. Okay, and so this is just basically showing you, okay, so we have ammonium chloride dissolved in warm water, ammonium chloride, okay? So warm water is gonna have more solubility. You can see everything is pretty much dissolved. We take that same concentration and we cool it down in an ice bath, right? So we start getting down to here, right? We have less solubility. So we have more stuff that's precipitating out. So the ammonium chloride is coming back together to form solid. You guys see that?
Mm-hmm.
Mm-hmm.
Okay.
What was that?
Sorry, I'm
Okay,
stuck with my son.
So now we get to do the math part of it, right? Okay, so we've already talked about percent mass, right? So all it is that mass ratio where we have, it's the mass of the solute over the mass of the solution, right? So we know that the solution is a combination of the mass of the solute plus the mass of the solvent added together. See, just like we talked about. And you guys are experts at this, right? Okay, so let's start with this problem. Who's going to be my volunteer? Who's going to do it for me? Okay, I guess I have to volunteer. Andy. Where you at, Andy? Andy, are you there? Okay, since Andy answered for you, Ro, you get the answer for Andy.
Ro's not here now.
Yes, he is. I see him.
When did Andy answer for me?
Earlier, I was saying, Ro, you got this, right?
Oh, I was in the bathroom.
Okay, so you get to answer this one. So I'll read the question and you help me through it. It says 125 grams of solution was evaporated to dryness. 42.3 grams of solute was recovered. What was the percent concentration of the solution by mass?
Hold on. So I start with what I'm given with, right?
Okay, so what are we given?
We are given. The 125 grams of solution.
Okay. And?
And 42.3 grams of solvent was recovered.
Okay. So then how do I calculate the percent concentration of solution by mass? what is the definition of percent concentration of solution by mass?
Oh, I'm gonna have to divide something, right?
Yep.
Oh, I'm looking at my screenshots.
Percent contribution by mass.
Oh, there's Andy.
Oh, he's back.
Oh, no. He answered for you, so you get the answer for him. Nope.
Oh my god. Okay. So
Oh, you told me earlier.
I was in the bathroom. Hey, nature called, so I had to answer.
Is it mass by solution and solution by mass?
So am I dividing 42.3 into 125?
Yeah.
Okay. And what else am I doing?
And divide by
Times 100.
Hold on.
time
Let me
100.
do that first. And I'm multiplying that by 100.
That is correct.
Baby.
And does it become 34% or is it 33.8?
36 fix.
33.8.
Okay. Piece of cake?
No, let me save it.
Well, when you walk me through it, yeah.
I didn't walk you through it. You told me. You walked me through it.
You're being too
I
kind.
just sat here and looked pretty. That's what I'm good at. Okay. Any questions? If you have any questions, you can ask Ro. Ro knows.
That's not true. Rose water. Rose a hoe.
In your carbon if you're a hoe.
Oh, so I destroy families, but I'm not a hoe. That's good, I guess. I'm a home wrecker, but I'm not a hoe.
Okay, it says, so you're to prepare 2.50 times 10 to the 2 grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? The density of water is 1.00 grams per mole. Let's see. I think I am gonna go with Marcel. Are you there?
Jesus.
Yes, I'm here.
Okay. So what do we need to do?
I'm not sure.
So when in doubt, what is the first thing that we should probably try to figure out?
Given.
Get the given.
Okay. So it says, what is our first given here? We're to prepare 2.0.
2.50.
Okay. So is this going to be, oh, wait, it says 2.50 of a 7.00% by mass sodium carbonate solution. So this will be my, how much solution I have, right?
Yes.
Okay, so my solution is going to be 2.5 times 10 to the second, or 250. Okay, and then it says, what is this? Is that our percent mass? Okay, so we got two things that are given to us. So what is the definition of percent mass again, Marisol? Mass of what over mass of what? Karina, you gonna help your road? You gonna help your road dog out?
Mass solute over mass solution.
That's right. The mass of the solute over the mass of the solution.
Times 100.
Times 100. Oops. Okay, so we know what the solution is because this is our solution. That's my abbreviation for solution. So if I plug that in, can't we just solve for the mass of the solute?
Yes.
Yes.
Solute. So solute is going to be equal to 7%. Divided by 100 times 250 grams. So what do you guys get?
17.5.
And the units?
The grams.
Of our sodium carbonate?
Wouldn't it be?
Wouldn't it be?
Nope, never mind.
How did you go from that third row to the second row? I mean, to the last row.
How did I go from here to here?
Yeah.
So I had solute over here,
Mm-hmm.
right? So then if I multiply both sides by 250, multiply both sides by 250, that's going to cancel out. Then I'm going to have 250 times 7.00. And if I divide both sides by 100, which I divide this side by 100, this is going to cancel out, and I'm going to get solute all by itself. Yes.
What is this called and what chapter is it?
This is chapter 16. And what did you ask me? What was the second part?
What is it called?
What are you doing?
Yeah.
So you were calculating percent by mass.
Calculating percent by mass. Thank you.
Yes. So this is basically solutions. You're working with solutions.
Okay.
I gave him that to chew on.
Okay, so then that gives me my grams of sodium carbonate. That's part of it. Now, what is the so what is the volume in milliliters of water are we going to use?
Aren't we going to subtract the solution?
That is correct. So we're going to subtract the solution. So which was 250 grams. And what are we going to use to subtract from it?
The 175?
Or 175.
You need 17.5?
Yeah. 17.5.
Equal. 5 and then 9 to 1 to 9. No.
We have 3 sig figs, correct?
So this is addition and subtraction. So then what would it be?
It's the 250 minus 17. 232.
It's still going to be 3 sig figs, but
232.
233.
Oh, because it's 5. 5 you go up again, and once you go up to 6. Okay. Oh, okay. You go with the 5. Because it always
technically it's you guys got 2. It was 232.5.
Yes.
Yeah.
And there's nothing behind it. So actually Andy would be right. It would actually be 232. Because there's nothing following it. It's right at that. Midpoint.
Oh, it's because when he gets excited, he pees. Like he sprinkles. I notice he does it a lot.
I do not sprinkle.
No, he said the dogs. She said the dog.
Let me take a picture for this one.
Okay.
So,
and then how do you change that to milliliters?
Just 1-to-1 ratio.
Milliliter?
232 milliliters of H2O.
Oh, it's the same?
I have a question.
Then convert it. You don't have to convert. Oh.
We use the density of water, which is 1 mil per 1 gram.
Oh, okay. Let me convert them.
Okay, what is your question, Ro?
Internet no good today. One gram equal how many?
By the way, good job, Karina and Marcel. That's why you guys work on the lab together, huh? Tag team. What was your question, Ro?
You answered it.
Okay. Okay, can we move on? Everybody got it?
Hold on, let me save this to.
Got it.
Take a picture.
All right, we're good.
No. I'm saving again. Okay, thank you.
I'll be back. I'm gonna go get me a snack. Okay.
Okay, we're gonna talk about 8 million things. Let me get back. Okay, okie dokie.
It said 233 on the answer.
I know, but it should be 232 because there's nothing following the 0.5. So it's my bad. I always like rounding up anyway, so. Especially if it's my paycheck.
Yeah.
So, molarity, okay? So molarity is defined as moles of solute divided by liters of solution. Now, it's not liters of solvent, but it's liters of solution, okay? So that's going to be important. Okay, so you guys ready to use this? You got it tattooed on your chest?
No.
Put it right now.
I'm good. I'm ready.
You look like you're ready to fall asleep. You don't look like you're ready for chemistry.
Dr.
Get
Henry.
too comfy.
Dr. Henry, I finished this and it did nothing to me. And this is the second one today.
See, I would be bouncing off the
Not the
walls.
original one.
Oh, it literally does nothing to me. I'm about to drink a bang.
It's not the original one.
It's not the original one. I don't like the original one. It's gross.
Oh, really?
Yeah.
Okay, so Stephanie, since you know about the original one, we're gonna have you do a problem. Okay.
Okay.
The problem says calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting to 1.00 times 10 to the second milliliters, second power milliliters.
So would I would be using the moles over liters, right?
Okay, so we're going to be using molarity, which is moles over liters.
So first I make sure what my givens are, and that is 15 grams of NaOH water, and then the 1.00 times 10 to the second milliliters.
Okay.
So, I need to convert the milliliters into liters, right?
Okay, so let's do that.
Okay.
Would you have to calculate the molar mass of NaOH also?
That is correct. But let's do one of them at a time because I can't do them both at once. My brain is good, but not that good. Okay, what do I do?
Okay, so you would put the milliliters in the bottom because we're trying to get rid of that. So 1,000.
1,000 milliliters for every liter.
Yeah.
Mil. Because we've been talking about it since the beginning of time. And mil means 1,000 in Spanish.
Wait, the solution is NaOH, right? Like
It's a solution of NaOH, yes.
Oh, okay.
So I'm just being lazy and not putting the solution part.
Okay.
Okay, so then this is going to cancel out. And we get
0.100 or 1.00, 100.
okay. Next. What are we doing next, you said?
Calculate the molar mass of NaOH, which is going to be 40 grams. $16 and 1.
Okay, what are we going to do with this, Stephanie?
You're gonna do dimensional analysis with
Starting with?
Starting with, oh, would it be with the 0.100? Oh,
Nope.
the 15 grams. Oh. So I put my 15 grams of NaOH as my given. And then with that, I'd put I'd put the grams in the bottom because that's what I'm trying to get rid of.
Okay.
Okay. So that means that one mole, right?
Yep.
1 mole would go on the top, meaning 1 mole is equivalent to 40 grams of NaOH. And that would be 0.38.
Moles.
Well,
So then do we now use the molarity solution that you told us to tattoo?
That's right.
So mole over liters.
Okay.
so it'd be 0.38 divided by 0.100.
How many sig figs should I have?
2.
.8, right? It would be 3.8.
Right.
3.8 moles over liters.
Or we put a capital M.
So
And sometimes you'll see it with a line drawn underneath it. Sometimes.
So that the capital M represents molarity.
That's correct. And then you put.
Try another one?
What was that?
Can we try another one after this?
Sure. Piece of cake?
Yep.
Yeah, kind of.
Yeah, kind of.
I mean, I'm understanding what I need to do now.
And understanding is the first part.
Yeah.
Okay. So let's try another one real quick. Let's say, did everybody get this down? I'm sorry.
Yeah.
Bro?
He's still grabbing his snack, Dr. Henry.
You better be cooking a full course meal as long as it's taken. Okay, so let's try this here.
Dr. Henry,
Yep.
for our lab, we also have to calculate the molarity, right?
For your lab,
Yeah, for the Kool-Aid one.
I have to think about it. I think you guys are just calculating, wasn't it just percent volume?
I can't remember.
I have to look again. So I think it was just percent volume that you're doing the calculations for. But now you know how to calculate it, right?
Yes.
Okay, so first we're gonna change the milliliters to liters.
Okay.
So we're gonna do 5.00 times 10 to the 2 milliliters solution. And that's gonna be times 1 liter over 1,000 milliliters.
Okay.
And that equals 0.500 liters. Bless you.
Bless you.
Yes. Okay, you gotta wait.
Oops, I'm just putting lines everywhere. Okay.
Okay, and then we need to find the molar mass of lead chlorate. So lead chlorate is BP or PB, sorry. And then in parentheses ClO3, and then outside the parentheses 3 subscript. Hold on, baby, in a minute, okay? So lead is 207 grams. Right. Yeah.
207?
Yeah, I think so.
207.
Okay.
207.2. So I just rounded it to 207.
Okay.
Chlorine is 35 times 3, so 105.
Isn't it like 35.5?
It's well, 35 times 3 is 105.
I mean, isn't it 35.5?
Oh, it's 35 point. What am I looking at? Chlorine 35.45. Yeah.
So then that'll be like 106, right? 106.5. Okay.
And then oxygen is 16, so 16 times 9.
$144.
1,000.
And then that's 457.7.
Plus 12, what?
Oh, no.
So then you would use that to find your moles of lead chlorate.
Okay.
So you would take the 50 grams of lead chlorate, 50.0 grams.
207.2 plus 126.5. Dr. Henry, how come I get...
And then on the bottom would be that 457.7 grams. Over, and then 1 mole on top. Sorry, do you have a question, Andy?
Yeah, how come I get 478? Let me do again. 144 plus 126.5 plus 207. Yeah, 207, right?
207 plus 106 plus 207.
106.
106.
I say 126.
Oh my god, I'm wearing earphones and that.
My eye choked up.
And that, that equals 0.109.
Man, you got me, doctor. 126.
Okay, so you said it's one point what?
Is 0.10 or yeah 0.109 moles.
Then this lower solution. I got it there.
And then you would take that 0.109 moles and plug it into our formula. So it'd be the 0.109 over 0.500 liters.
Okay.
And that equals 0.218 molarity of lead 3 chlorate.
Okay. You said 0.2.
I gotta save this one too.
Okay, piece of cake.
Yes, no. Stand so far away, that's right. 126.
Okay, you guys ready for the next one?
Yes.
Yes.
Good job, Chris.
Thank you.
Good job. I go.
Okay, everybody got a picture?
I got a picture.
Okay.
Hello, you.
Everybody else awake?
Whoa.
You may want to save it for Ro.
I saved it.
Yeah.
I got it.
Saved it?
Oh, okay, you got it.
Good. Thank you. Appreciate it.